So we denote by OI the ith row of matrix O, and I will turn this equation into a relation involving dot products of any two rows. So let's write this one as, I believe I wrote down this earlier also, OIK, and O transpose KJ will be OJK, okay, and this is delta IJ. Okay, so if I am denoting by OI the ith row of I, then this is a dot product between the ith row and the jth row. Okay, so I can write this down as OI dot OJ delta IJ, which is just saying that if I is not equal to j, OI dot OJ is equal to 0, and also if you put I equal to j, then you have OI square equal to 1. Okay, meaning that any two rows are orthogonal to each other, and each row represents a unit vector. Okay, so these are all normalized to 1. So that's the property of orthogonal matrices. So let's say if someone asks you to construct some orthogonal matrices, all you have to do is search or construct n orthogonal vectors, make sure that they are normalized, and just arrange them in a matrix form, and that's what will give you an orthogonal matrix. And the same holds true for column vectors as well. Okay, whatever I have said here also holds true for column vectors. Okay, that's good. I'm pretty sure this was familiar to you already. Now let's move on to quadratic forms. So let's go to the next page. So you are often going to encounter quantities of this form. So you'll have, let's say, how should I write? Yeah. Let's say a matrix A whose entries are A, I, or I think I was more commonly using alpha and beta. Okay, let's say whose entries are, yeah, doesn't look good, so I will write Aij, and this matrix is sandwiched from both sides by some row and column vectors, which we denote by x, and whose elements are xi. Okay, then this quantity is called a quadratic form. So here there is a summation over all I and j. Okay, I'm looking at n dimensional vectors and n cross n matrices. Okay. Now this is called a quadratic form. Okay, and of course your Aij's, they will form a symmetric matrix. Now there is a theorem here which says that I can always okay, let me write it down first. Transformation to principal axes. Quadratic forms. So that's what we want to discuss now. Transformation to principal axes of quadratic forms. So what I mean by this is that we can always choose axes such that the quadratic form here, this becomes a sum of squares. Okay, so here what you have is a quantity which involves cross terms also. So let me write it down more explicitly. If you look at it, let's say I look at a11 x1 square. Okay, that's fine. Let's look at term a12 x1 x2. Then you have a term a21 x2 x1, which is again x1 x2, and so forth. Then you will have a term which will have x2 square, something here. Okay, so in addition to these terms which are squares, you also have cross terms. Okay, and the claim is then that I can do a transformation such that this quadratic form will appear only as a sum of squares. So it will involve only squares like this and not involve any cross terms. Okay, and clearly this is going to be through orthogonal transformation, because your A has to be a symmetric matrix, and you already know that you can diagonalize an symmetric matrix by a real orthogonal transformation. Okay, so that's not a surprise that we can put this quadratic form into sum of squares. Anyway, let's do it. So proof. So the proof of the theorem is the following. It's trivial actually, but anyway it will help to. So let's say A I j x I x j I can write as, let's say I denote a vector x, okay, which is a row vector. Matrix capital A is the one which corresponds to these entries, small a I j. Let me put transpose here, x. Okay, so that's what we have, and I'm saying I can do a transformation from x to y, which is related to your x column vector by some orthogonal matrix O that you can do, that you can choose, and I'm choosing this O to be the one which will diagonalize the matrix A. Okay, so the choice is such that this guy or this guy becomes the following. So I can write x trans, not small x but x transpose A x is equal to x transpose, here is our A, here is our x, and I want to put O here, O transpose here, O transpose. Okay, where O is an orthogonal matrix, so O transpose is identity. This is 1, so I have done really nothing. Okay, I have just inserted identities, so I have not changed anything. Now this O is 1, I have chosen that O which diagonalizes this matrix A. So what I am left with is x, let me skip okay, let me do it in 2 steps. O transpose, and then you have A diagonal. Okay, so the diagonal matrix corresponding to A, and then you have OX. Let me, I've already defined this to be Y. I should have written a capital Y here. So anyway, this is Y A diagonal Y transpose. Okay, this is, if you write in terms of components, so Y is a column vector. It will have entries y1, y2 and so forth. So most generally, in general you will be able to write this as the following. Let's say the diagonal entries of AD are E1, E2 and so forth. So you have E1 y1 square, I should remove the sigma, so E1 y1 square okay, I have assumed that none of the E's entries on the diagonal are 0. but it's not a problem if they are. It's not a problem if they are repeated. Even if they are repeated, it's fine. So okay, yeah, so I can put any quadratic form into sum of squares. That's what I have done, which is nice, which will be very useful. Okay, and it's also clear, and if it is not, then you sit down and convince yourself that these EIs are the eigenvectors, sorry, eigenvalues. Eigenvalues of the matrix A. This, okay. And also convince yourself that the transformation which we have done, this orthogonal transformation that you have done, puts your coordinate axis, okay, along the eigenvectors of A, okay, and these eigenvectors are called the principal axis vectors. Okay. Okay, all good. And yeah, because A is a real symmetric matrix, all the eigenvalues are real, and that's why all your EIs will be real, so you'll still be in the real space. That is one thing. Okay, fine. Let's see what else I want to say. Okay, good. I hope I did mention it, but if not, let me repeat. All the AIs, AIJs, these are just some numbers. Okay, these are all constants. Okay, very good. So now I want to say a little more about this. You can imagine that if I do a little bit more, if I do a further transformation, I can not only put this in a form containing only sum of squares, I can just do away with all the EIs, so that all the coefficients are unity. Okay, that's what I want to do now, and of course for that I have to okay, do a transformation which will not be orthogonal. You'll see that in a moment. Okay, so I want to make an assumption that matrix A is positive definite. Okay, if A is positive definite, then you will have n eigenvalues which are non-zero by definition, and that is what I want to have. So I want to have a sum of squares in exactly n variables. So I don't want to have a situation in which I have y1 square plus y2 square, e1 y1 square plus e2 y2 square, so on and so forth, up to em ym square, where m is less than n. That is not what I want. I want m to be equal to n. Okay, so that's why I'm looking at a positive definite matrix, which you will realize why I'm doing this in a short while. Okay, so if I do so, and as I have already said, that I can always put Aij xi xj into the following form. Summation is implied, Einstein summation convention is being used, so I can put this into the following: e1 y1 square. That's what we have just now shown. This is the principal axis theorem. En yn square. Okay, assuming positive definite. Now clearly, if I define or do a further transformation and I take these yi's to zi, where zi is related to yi by the following. Okay, if I do this, then what will happen? I will basically be absorbing these ei's into the yi's, okay, which is what is zi now. So this will turn into this will become z1 square okay, and there is no problem because all of the e's are positive. Okay, so you don't end up with something complex, which is good. Okay, now let's ask whether this is achieved by an orthogonal transformation. So we have done two transformations. One transformation with that orthogonal matrix O, which put into this form, and then on the top of it we have this transformation. And I hope it's clear that this is not an orthogonal transformation. So let's see it more explicitly. So what we have done is gone from X, let me again put more in terms of column vectors and matrices directly, from X transpose AX, we went to, as I wrote before, we transformed this to A diagonal, which was O transpose O, and then you have here Y, right? You had OX, which is Y, so you reached here. I should be writing this as, okay, if I'm not putting an index, it's clear that it's a row or a column. And then we did something which is this, which is basically this transpose this matrix you have anyway, and you had your Y, which I'll write down. Let's insert the following: 1 over square root of E1. So these are all on the diagonals. Okay, these are diagonal matrices. Okay, square root of E1 En. Okay, you have Y1 Yn, and then here again you have 1 over square root of E1 okay, En. This is nothing, and then you have Y transpose, so basically the row Y1 to Yn. Okay, so from here to here, this is what is your Z, right? This is your Z, that's what we wrote earlier, and this is your Z transpose, and your transformation is really this one. This was A. And you see this is not an orthogonal matrix, this one. So this entire transformation, O transpose times this thing, is not an orthogonal transformation. Why is this not orthogonal? If you take a transpose of this, it will give you the same thing back, because these are the diagonal entries. And if you multiply together, you get 1 over E1 and 1 over E2 on the diagonal entries, not unity on the diagonal entries. So this is not an orthogonal transformation. Okay. Okay, that's good. And why all this is useful and interesting to me, I'll tell you now. So here's the point. In general, if you have two symmetric matrices, okay, you cannot diagonalize them simultaneously. You can if they commute, okay, but if you have two positive definite forms, like what you have seen just now, if you have two positive definite forms, then you can diagonalize them simultaneously. In fact, what you can do is, okay, let me be more precise. If you have two quadratic forms, one of them is positive definite, if that is given to you, then you will be able to put both of them as sum of squares. In fact, what you will be able to do is, you will be able to put the the quadratic form that is positive definite as a sum of squares with unit entries, what I have just shown to you here, okay, and the other one will be diagonal with non-zero, with coefficients which will be not equal to 1. Okay, this is what I want to show now. That should be quite obvious to, more or less it should be obvious now, that we can really do such a thing. So let me go back, go further. So what I want to show is simultaneous diagonalization of two quadratic forms one of which is positive definite. Okay, so let's say you have the following. Let's say you are given two positive two quadratic forms, aij xi xj. There is a summation over I and j, and it runs from 1 to n, plus another quadratic form bij xi xj, again summation. There is a summation, and I am claiming that I can put it as zi square summation over I. Let me put summation plus let me not use zi, I will use ni or eta I square, okay, plus some b prime I want to use, I think. Let's say Cij eta I square. That's the claim, provided Aij is positive definite. POSITIV, positive definite matrix. I mean, you can also say this is a positive definite form, either way. Okay, so let me just say in words why this is going to work out. So it's going to work out for the following reason, which we will, I'll write down some equations to show you. So look at the first one. This, I have shown that in the previous in last few minutes, that I can put this in this form. Okay, let's say I can put this as sum of zi squares. Let's not use eta. So I am saying that I can do a set of transformations, not orthogonal of course, and it will put this into the following form, into zi square. I should, now that I am putting sigma, I should put here also. Okay, this is what I have already shown in last few minutes. Now once you have done this, this guy Bij xi xj would also transform to zi zj some b prime. Okay, this is what will happen. Right, so you have done a change of basis, your x's have changed to z's, and the matrix Bij would transform into some other matrix, and it will, we are calling that b prime, and this b prime would also be symmetric, so you again have the same situation as before, meaning now you can do one more transformation and you go from z to eta such by an orthogonal transformation such that the b prime, the matrix b prime, gets diagonalized. Okay, so from z you go to eta through an orthogonal transformation which will diagonalize b prime, which will mean that this piece will be put into sum of squares. Then you may worry, what happened to this, what happens to this part then? Nothing will happen to this, because this is a sum of squares. Under orthogonal transformation it will still remain a sum of squares. Okay, so that will prove my assertion that we can simultaneously diagonalize two quadratic forms if one of them is positive definite. Let me write some steps so that it is more apparent, but I think I have already explained this. Nevertheless, let me write. So as I said, after reducing the first piece to sum of squares with unit coefficients, I would end up with Bij xi no zi zj zj. Okay, and this is summation over I j, and there's a prime. Okay, that you agree. If you are not clear why b will be again symmetric, sit down and just check whether you are fine with that assertion. Now let's do, so the matrix I will denote by b prime, and the entries by small b ij. Okay. Okay, good. So what we have to do is, now we will go from here to the following. So this is b prime z transpose z. That's what you have, right? This piece. Now let's say b prime gets diagonalized by O. So I am going to OZ, O transpose, and this will be an orthogonal transformation because it's real symmetric matrix b prime. O transpose Z transpose. Okay, this I call eta. This will be eta prime, eta transpose, and this will be your b diagonal. Okay, so good. So this piece becomes eta I, eta j prime, b prime diagonal, and which I want to call as matrix C, whose entries will be Ci j. Okay, so it whose, so because this is already diagonal, and let's call these entries as Ci's, so you get eta I square Ci. Okay, because it's diagonal, that's what you are going to get. And here what has happened, let's look at this piece now. Your Zi square is Zi summation over I, or which is same as Z transpose Z. And what has happened to Z? We have put O transpose Z, and this is what you have called eta. This is eta transpose, and you clearly see you don't pick up any coefficients. It just remains eta I square. Okay, it still remains the sum of squares. So what you have here is the entire sum becomes eta I square plus ci eta I square. Okay, that's good. So this is what all I wanted to say in this quick review of some of the mathematical things which we will require. I think that is sufficient, and we will continue with not continue, we'll start looking at small oscillations in the next lecture. See you.